A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians, welcome back to another video. We now got double pendulums and gyroscopes over on stemword.com. Check it out, links in the description. So, a lot of you guys actually really enjoy this type of video where I take 4 relaxing problems over from brilliant.org and put them into a small video where you can try the problems out for yourself at first and then keep watching the video for the solutions. And this is one of these videos, 4 relaxing number theory problems that we are going to deal with today. Like mentioned at the start of the video sponsored by Brilliant. Overall, you can find out more about Brilliant at the end of the video, but more importantly, I found those problems also over on Brilliant, and they give you a wide variety of problems, be it competitive math problems, physics problems, etc. over on their website, and I actually found those problems in their great community created problems, and you can find so many over there, and it's just absolutely amazing. So definitely, if you're interested in way more mathematics problems, check out the sponsored message at the end of the video. And I'm going to show you the problems. You can try them out for yourself and then keep watching the video for the solutions. So those are the first 2 problems that we are going to solve. Okay, pause the video, try them out for yourself. And those are the other 2 problems that we are going to take a look at today. I hope you were able to read all of those. And now here come the solutions, at least the ones that I have figured out for myself. And the first one is asking for the sum of all n such that n to the 3rd power minus 8n squared plus 20n minus 13 is a prime number. And this one right here is a nice little Diophantine equation that we are going to solve. And at first, let's remember what it means for a number to be prime, or just for a Diophantine equation to yield some kind of prime result. Namely, a prime number is an element which only has 1 and itself as a divisor, or a unit and itself. Meaning, if we were to turn this right here, this polynomial, into some kind of multiplication of 2 factors, then we could set n equal in one of those factors such that it actually gives us the number 1, and this is basically the thing you want to strive for here in this problem, and this is what we are going to do at first. But how would you go about factoring this polynomial? Well, one thing you might notice is that 1, the number 1, is a root of this polynomial right here. So if we were to plug in 1, we're going to get 1 minus, 8 is going to give us negative 7, 20 minus 13 is 7, 7 minus 7 as additive inverse gives us 0. So this right here is actually a 0 of this polynomial, and now we can start doing polynomial division basically. Meaning what we're going to end up with is that we got n to the 3rd power minus 8n squared plus 20n minus 13 to be of the form n minus the root that we just now found out times a n squared plus bn plus c. Okay? This right here is going to be the polynomial that we are going to get out on the other side after doing polynomial division, and we can find out a, b and c by just comparing coefficients after factoring everything out. One thing you might notice is that this right here is actually just a monic polynomial, meaning the leading coefficient of n to the 3rd power, so the highest degree of our polynomial, is actually 1. So if we were to multiply n with a n squared, we are going to set a to be equal to 1 because the leading coefficient right here is actually equal to 1. So we got rid of the a. Hey, that's pretty good. Now you can start factoring everything out. But you can actually see another one of those coefficients that we got here at a glance. Namely, what about the negative 13 that we got here? I mean, if we were to factor everything out, if we multiply everything with an n, those are all the factors that we have with some kind of n in here. So the only way to get to our negative 13 in some way is to multiply the negative 1 with, n squared includes n, bn is going to include n too. Oh, we are going to get negative c out. Negative c is the one without the n basically multiplied with it. Meaning, if we get negative c to be equal to negative 13, we can actually conclude that c must be equal to 13. Okay, and now we can also plug our c into here, so plus 13. And all that's really left to do is to basically factor out this polynomial and then just see what our b must be equal to. Let us do this real quick. Meaning, our polynomial that we get here is also equal to, multiplying n into here gives us n to the 3rd power, plus, and then we are going to get b n squared, and also we are going to get plus 13n, and then negative n squared. Also we are going to get negative bn, and then negative 13. Okay, and now we can just start gathering powers of n together equally. So for example, on our n squared, we are going to have b minus 1 if we factor everything out. So this is n to the third power plus b minus 1 times n squared. And also the other ones that we are going to get is 13 minus b times n. So plus 13 minus b times n and then negative 13. And yeah, now we are basically good to go because we can now compare coefficients. I mean, b minus 1 must be equal to negative 8, and we also have 13 minus b must be equal to 20 if we were to compare coefficients with the original polynomial. And yeah, it's quite easy to see that b must now be equal to negative 7, okay? Because 13 minus minus 7 is 13 plus 7 gives us 20, and also here negative 7, negative 1 is going to give us negative 8. Meaning overall, b must be equal to negative 7. And this is good, we now factored our polynomial. Meaning our polynomial n to the third power minus 8n squared plus 20n minus 13 is actually equal to, okay, n minus 1 times, and now we are going to get n squared, and b is negative 7, so negative 7n. I'm going to get rid of this line real quick, and also last but not least, plus 13. And now we can start saying, okay, this number is only prime, so just some p prime, if one of the factors is equal to 1. Meaning, on the one hand we get, okay, this is the first factor, n minus 1 must be equal to 1, meaning overall we get n being equal to 2. This is one solution that we can actually get. Or we are going to say that n squared minus 7n plus 13 is also equal to 1. And now we can just start solving a quadratic equation right here. And n must be equal to something positive because primes are defined to be positive, okay, overall. So if our n were negative, then we would possibly get a negative solution when plugging it into here, and primes are defined to be positive numbers. So we are only going to consider the principal branch basically of the solution here. Meaning overall, if we were to subtract 1 on both sides, we are going to get a 12 here, being equal to 0. Now we can start using the quadratic formula on this problem. Leaving us overall with, okay, our solutions n, 1 and 2, are going to be equal to, okay, we are going to get 7 over 2 plus minus the square root of, okay, we get 49 over 4, and then we are going to get negative 12. Now we are just going to expand our negative 12 by 4 over 4, obviously, giving us 48 over 4. Okay, if we were to subtract this, we are going to get out that this is 7 over 2 plus minus, and inside our square root we are going to get 1 over 4, 1/4. Taking the square root of that is going to give us 1/2. So meaning we are going to get two solutions out on our n, with the first solution being, and both are positive, this is good, so even though we are only considering the principal branch, since we don't get out a negative number, we can consider both branches here, which is pretty good. Okay, it really depends on the problem that you are dealing with. On the other hand, we are also going to get that this is 8 over 2, this is the first branch, giving us 4, okay, meaning n can also be equal to 4, and the last one is going to be 7 minus 1, which is going to give us 6 over 2, which is 3. So those are the only three values for n that we can actually have to get a prime out on the other side when plugging this into our polynomial, and the sum of those three is going to give us 9 overall, meaning the solution to our problem is going to be 9. That was kind of exhausting, that was way more elaborate than you might have thought from the get-go, but still a pretty relaxing question. Next up, is the smallest n such that n factorial divided by 12 to the 12th power is element of n? What does it mean for a fraction to be element of natural numbers? Well, it just means that if we were to divide n factorial by 12 to the 12th power, we are going to get a number like 3 or 5 out on the other side. Meaning, since n factorial is a product of things, we want to have 12 times 12 up here inside our factorial, such that all the 12 12s down here are going to cancel out in the process. But let us manipulate this problem a tiny little bit further, because we can actually turn all of this into prime factorizations overall. Meaning, 12 is nothing other than 4 times 3, and 4 is 2 squared, leaving us overall with the question when n factorial divided by, okay, now we get something to the 12th power. What is this? 2 squared times 3 to 12th power is element of n. Or in other words, if we use the properties of exponentiation, we're going to ask ourselves when n factorial divided by 2 to the 24th power times 3 to the 12th power is element of n. Well, what does it mean? Okay, rewriting this problem. What we want is we want to find out the smallest n such that we are going to get 24 teeth up here in our factorial as factors, and also 12 threes up here as factors in our factorial. And now it's time to start brute forcing it a little bit, okay, because we're just going to count through all the n's up until we reach the smallest point. I couldn't find any other method to do so, so yeah, we're just going to do this. If we count twos, okay, every second number is going to include a 2, every even number, but don't forget every multiple of 4 is going to include twos, and every multiple of 8 is going to include 3, and every multiple of 16 is going to include 4 twos. And now we're going to start counting. Okay, each and every even number, 2, and then we are going to get 4. Okay, 4 has 2 factors of 2. Then we are going to get 6, then we are going to get 8, has 3 twos. Then we are going to get 10, then we are going to get 12, but 12 has a factor of 4 in there, so 2 twos, gives us 10 at first. We are at 12 right now. Then we are going to get 14, then we are going to get 16, which has 4 twos. Okay, we are at 15 now. Then we are going to get 18, only has 1 2. Then we are going to get 20, which has a factor of 4 in a 2 twos. Then we are going to get 22, and after that we are going to get 24, which has a factor of 8, meaning this gives us 3 more. We are at 22 right now, and then we are at 26, and after that we are at 28. So maybe n equals to 28. Okay, is going to be the smallest n for which this holds. But now let's count our threes. We need 12 threes. And don't forget, every multiple of 3 gives us 1 3, and every multiple of 9 gives us 2 threes, and every multiple of 27 gives us 3 threes. Okay, 3 threes. So let's start counting. We were at 28. Let's see if this holds. 2. So we got 3, we get 6, we get 9. And after 9 we are going to get 12, then we are going to get 15, then we are going to get 18. Okay, 18 is going to give us 2 more 9s, okay, 18. After that 21, then we get 24, we are at 10 right now. And after that 27, hey, this holds, okay. Now we are good to go, meaning n equals to 28. Is going to be the smallest n for which this right here holds. And then, and thus we are done with the next problem. This was kind of a brute force problem, but yeah, it worked. And now we are kind of at the same problem once again here with the trailing zeros of, okay, and we are going to multiply the floor of 1 with the floor of 2 with the floor of 3, blah blah blah, up until the floor of 100. What does it mean for something to have trailing zeros? Well, we just want to look for the powers of 10 in here. So a number, for example, has 5 trailing zeros if it has a factor of 10 to the 5th power, okay? Meaning we want to see how many 10 to the nth power we have, and then we have n trailing zeros overall. Now, what does it mean to multiply floors together, like floor of 1 and floor of 2, floor of 3, etc.? Now the good thing is, the floor of a natural number is just a natural number in itself. If we round down from 2, we are going to get 2 overall. So this problem is going to reduce to 1 times 2 times 3 times 4 times blah 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 up until 100. Well, and now we can just start counting tens. And what is the prime factorization of 10? It's basically the same thing as we did here. Prime factorization of 10 is 2 times 5. I mean, we have a lot of 2's in here. You see, we already have 24 2's in here, and just counting up to n being equal to 28. So what we just need to do is we need to find out how many 5's we have from 1 to 100 as factors. And basically each and every 5th number is going to give us 1 5, with the exception of 25, which is going to give us 2 5's overall. Okay, 2 5's because 5 times 5 is 25, and each and every multiple of 25 is going to give us 2 more 5's. Meaning from 1 to 100, okay, 100 divided by 5 is going to give us 20 5's overall already. Now we got 25's at this point, but in between 1 to 100 we are going to get 4 factors of 25 in there, okay, 2. Meaning to the 20 we are also going to add, okay, on 25 1 more, then 50, 75 and then 100. Meaning we are going to have 24 overall, so to the 20, we are going to take 4 more. We are going to have 24 5s in there. And yeah, we also have 24 2s definitely, because n equals to 21. It's also going to give us 24 2s, meaning overall we are going to get n being equal to 24, 4, 10 to the nth power as being our factors in here. Okay, we're going to get 24 trailing zeros. And yeah, this is already the problem. Once again, this has been a little brute force problem, but it's a nice thing to think about once in a while. And last but not least, what we're going to do is we're going to rewrite this identity that we have up here. And before taking a look at the exercises, I didn't know about this identity, but it's pretty cool in my opinion. How can we simplify 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial up until plus n times n factorial? Well, what we're going to do is we're going to turn into factorials that we have right here into some kind of n plus 1 factorial. Let me show you how it's done. It's actually pretty cool. Took me a second to come up with the solution, but it's a pretty cool identity that I didn't know about before. So what we're going to do at first is we're going to say, okay, 1 is nothing other than 2 minus 1. Okay, taking 1 away from 2 is going to give us 1 yet again. So this first factor is going to give us 2 minus 1 times 1 factorial. Maybe you can see where I'm going at here, because if we were to multiply everything out, we are going to get 2 times 1 factorial, for example, and 2 times 1 factorial is the same as 2 factorial by the functional equation of the factorial. Next up, we are going to go through the same process. Successor of 2 is going to give us 3. How can we get back to 2? Well, 3 minus 1 is going to give us 2. So plus 3 minus 1 times 2 factorial. And once again, 3 times 2 factorial is going to give us 3 factorial in the process. And then we are going to get plus dot 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 up until, okay, next up, let me write out one more term. Okay, next up is going to be 4 minus 1 times 3 factorial. And then plus blah 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 up until, okay, next up it's going to be n plus 1. We are going to add a 1 to it and subtract it yet again times n factorial. If we were to multiply everything out, what we are going to get in the process is, no, just putting an equal sign here, it's going to give us, okay, 2 times 1 factorial is going to give us 2 factorial, minus 1 times 1 factorial is going to give us 1. And then we are going to get plus 3 times 2 factorial is 3 factorial, minus 2 factorial simply. And this is so cool, this is just a telescoping sum. Next one, 4 times 3 factorial is going to give us 4 factorial. So plus 4 factorial minus, okay, just 3 factorial. And then we are going to add a lot of stuff to it, plus, and then we have the n minus 1 term, blah blah blah, up until the, okay, n plus 1 times n factorial is going to give us n plus 1. Factorial minus n factorial. And here we are just going to get something n factorial minus n minus 1 factorial and so on. And now we are going to notice that 2 factorial is going to have an additive inverse here. 3 factorial 2, 4 factorial 2 in here, and so on up until n factorial is also going to cancel out, leaving us overall with a final answer of n plus 1 factorial minus 1, which is a pretty cool identity if you ask me, and I really like this last exercises. It has nothing to do with brute force, just thinking about the structure of factorials a tiny little bit more. And this concludes today's video, and like mentioned at the start of the video, if you want to see more math problems like this, if you're interested in dealing with a bunch of very cool sneaky problems, then definitely make sure to check out today's sponsors content. Brian for sponsoring, yeah, thanks to Brian for sponsoring yet another video here on this channel. Didn't know what I was saying there, but what you need to take away from my message here is that you should go over to Brian and check out the stuff that they post there. It's pretty amazing if you ask me. So to keep it nice and short, Brian is an online learning platform and app which gives you nearly 70 interactive courses to play with. Doesn't matter what you want to learn, physics, mathematics that we did today, competitive mathematics, chemistry, Python programming. They definitely got you covered. So it really doesn't matter where you are at right now in the STEM field, what you are studying right now, they definitely have something for you in stock that you could definitely find a use in. So even I found a lot of things that I didn't learn about before over on Brilliant, which was a real surprise to me, because I thought that I couldn't possibly learn way more stuff or just things I haven't done before at my university from an external source like Brilliant, which was a real surprise to me, but a really good one. And if you're not yet convinced that Brilliant is a pretty cool website, then you should definitely convince yourself by trying it out for free, at least a big portion of it, by using the link at the top of the description. And if you really think that the service is something that you would like to pay for, that you think has a great value to you, then you can use the link and get 20% of an annual premium subscription. So that's also a pretty great deal. The first 200 people to actually use the link get this discount. So yeah, it's definitely something you should take into consideration if you want to strive for getting way more knowledge into your head by using Brilliant. So definitely try it out and support the channel this way. If you enjoyed this video, please like, subscribe, and comment channel if you like. If you want to support the channel a bit more, buy those t-shirts I create to support the channel on Patreon. Also, don't forget to go over to Stanford for the new double pendulums. They're absolutely amazing. And up until the next video, I'm wishing you guys a flammable day. Ciao!